Section 12.1, Three-Dimensional Coordinate System. The objective of this section is to get familiarized with three-dimensional coordinate system, distance and midpoint formulas, basic graphs in R3, which means space, an equation of a sphere, and also at the end of the section we'll explore something called position, or I should say projection of a point onto x and xy and xz and yz plane. Projection means the shadow of a point. So with that said, let's get right to it. So before we begin, let's talk about these notations. R, R2, R3, Rn. So R stands for set of all real numbers. R2 stands for all ordered pair of numbers. So here we are basically on a number line, whereas up here we are on the x and y axis. Okay, and R3 is all ordered triple of real numbers. So here we are in three-dimensional axis. Okay, so this would be like z-axis, that would be y-axis, that would be x-axis, and these guys are mutually perpendicular. We'll talk about this in a minute. So the idea is as follows. So because we like to change this two-dimensional plane into a three-dimensional space, so what we need to do is add what? The third coordinate, which is the z-axis. So remember, this is basically what's happening is the floor. Now we're trying to what? Make this axis to represent a point in space. So therefore, we need an additional axis called z-axis. Basically, we have two ways of graphing this three-dimensional coordinate system. Either you do it by right-hand rule or left-hand rule. Basically, what it amounts to is if you kind of form your three fingers, namely what? Pointing fingers and middle finger and what? Thumb. So if you use your right hand, so what's happening is the pointing finger is the x-axis, the middle finger is the y-axis, and the thumb points out to the z-axis. On the other hand, if you use your left hand fingers, the pointing fingers points to the what? Y-axis. Now the middle finger is the x-axis, and the thumb is still what? The z-axis, as you can see from the diagram. So therefore, what we have is the following. So you kind of, we always, 99% of the time, we go with the right-hand rule. So if we just draw the what? Three-dimensional axis. So here is the z-axis, here is the y-axis, and here is the what? X-axis. And the origin now, it's 0, 0, 0, as opposed to just 0, 0 on the floor, which was a point on XY plane. But now it, every point in the space has three components, namely x component, y component, and the z component. So in xy plane, notice the axis divided the floor into four quadrants, namely quadrant number 1, quadrant number 2, quadrant 3, and quadrant 4. Turns out in 3 dimension, the axis divide the space into what? 8 octants. Okay, so how does that look like? Well, pretend you have what? A 2 stories house. So pretend that you have what? 4 adjacent rooms upstairs. Okay, so this would be like upstairs. And then exactly the same 4 rooms, what? Downstairs. Okay, downstairs. And that would be right below it. So remember, you have a total of 8 rooms. 4 rooms happens to be upstairs, and 4 other rooms happens to be right below the 4 rooms upstairs, downstairs. So what happens is you get 1, 2, 3, 4, 5, 6, 7, 8 octants. So this is pretty much how the rooms should look like. Notice. So what's happening is now we have these planes. So this guy is called YZ plane. Okay, this guy is called what? XZ plane. And this guy is the floor, which is called what? XY plane. In terms of a diagram, so that would be like the right wall, let's call that YZ plane. This would be like the left wall, let's call that XZ plane, and the floor would be XY plane. So the question is, what would happen, what's going on in these planes? Well, what's happening is in XY plane, any point happens to have the component of what? X, Y, but 0 for Z, because you are on the floor, so there is no height. In XZ plane, you have what? The point, let's call this point P1, point P2. This would be like what? X0, what? Z. And in YZ plane, the point will look like 0, Y, Z. In other words, what we're saying is, if you select a point in what? XY plane, the components of the point will look like this. Any point in what? YZ plane, the components of the point will look like this. Do you see it? Any point in the what? XZ plane, the components of the points will look like this. So that's pretty much how these 2 walls and the floor look like. So the idea is, what do you mean by projection? Projection is like a shadow. Okay, the shadow. What does that mean? That means if I, have a point in space, like let's say this point right here, X, Y, Z. And what I do is shine a light here and see the shadow of this point on the XZ plane. How would the shadow of this point will look like in XZ plane? Well, it turns out its shadow, we're going to call it P prime, it's going to look like what? X, 0, Z. So there will be no Y. Do you see it? If you shine the light this way from top of the point towards the floor, the shadow of this point on the floor, it will be X, Y, 0. So these are called projections of a point onto XY, XZ, and YZ planes. So the question is, how do you graph these guys? Well, let's go back to the coordinate system and make sure we understand the signs here. Okay. So what's happening is, if this is the z-axis, remember these are mutually perpendicular to each other. Remember, if you form your fingers like this guy is perpendicular to this finger, that guy is perpendicular to both of these. So they are mutually perpendicular. So what's happening is, this is the positive y-axis. This would be negative y-axis. Positive y-axis is known to be the right. Negative y-axis is known to be the left. Positive z-axis happens to be known as up, and negative z-axis happens to be down. Positive x-axis happens to be also known as front, and negative x-axis, which happens to be right here, happens to be known as back. So you got right, left, up, down, front, and back. So how would you go about graphing a point in space? Well, Let's see now. Suppose the point in space happens to be 2, 3, 4. So what do? You go 2 units along the positive x-axis. Remember, this is positive. That means you go 2 units to the front, 3 units right, and 4 units up from the origin. So 2 units to the right, front, 3 units right, and 4 units up. 1, 2, 3, 4, and you are in the space. So what happens is, every time you graph a point in a space, that would be like what? A corner point of a shoebox. So every point in the space happens to be the corner point of a shoebox. Let's do kind of like few more examples. Notice here, you go back, you don't move sideways, but you go up 5 units from the origin. So go back 1, and from here you go up 5. 1, 2, 3, 4, 5. Right there is the point Q. Do you see it? Here, here is the three-dimensional axis, Z, X, and Y. You don't go what? Back or front, but you go what? Left. So you go left 1, down 3, down 3. So left 1, down 3, right about 1, 2, 3, right about here. So that's point R. This guy is you go what? Front 1, right 3, and down 6. So that would be your what? Right-hand rule axis. So I'm going up front, 1 unit positive, 3 to the right, 1, 2, 3, down 6, 1, 2, 3, 4, 5, 6, right about here. That would be like point P prime. Do you see it? So as I mentioned last time, so these are the 2 walls and the floor, and basically those are the components of each of the point in each of the planes, namely xy, xz, and yz. All right. So remember, we said the coordinate planes, what? Namely, x equals 0, y equals 0, z is equal to 0. These are called coordinate planes. Divide the space into 8 octants. So what would be the sign of what? Each of these octants? In other words, if I have, let's say, a point x, y, z, what would be the signs of each of these components of the point in each of these what? Octants? Well, turns out in what? First octant, all the 3 components are positive. In the second octant, what? You got just like, you know, 2 dimension, like in the second quadrant, x is negative, what? Y is positive. In the third quadrant, they both are what? Negative. In the fourth quadrant, x is positive, y is negative. But in what? The first 4 octants, all the z components are positive. So remember, this is like the upstairs, the 4 rooms upstairs, correct? But now, what about the rooms downstairs, right below these 4 rooms upstairs? Well, you could imagine that what? It would be exactly the same signs for what? For x and y components. Okay. The only difference is because you are in the what? Downstairs what? Floor rooms. So the what? The z components would be negative. Do you see it? So the question is now, can you determine the octants in which each of these points are located? Notice all of these guys are positive, so this point must be in the first octant. Okay, x is negative, y is negative, but z is positive. So you must be in what? This point must be in the third octant. Remember, we don't say quadrant, we say octant. Okay, What about this guy? X is positive, Y is what? Negative, Z is negative. So you are in the what? In the eighth or on the eighth octant. Do you see it? Because X is positive, right? Y is negative, so is Z. So you're in the what? Eighth octant. So that's how you can tell in which octant the points are located. Incidentally, just for laughs and giggles, let's just graph this guy. So you go what? Back -1, 3 units left, and 5 units up. 1, 2, 3, 4, 5. Right here is your point P2. This is your 0, 0, 0. Remember, most of the time we go by right-hand rule. So this is the y-axis. That's the z-axis. That would be the x-axis. Distance formula between 2 points in R3. Remember, R3 is just a notation for space. That means three-dimensional coordinate system. So given 2 points, like let's say 2 opposite corners of a shoebox, how would you find this distance? Well, turns out it's exactly the same as distance between 2 points on xy plane, except now you have to add the z component. The way this comes about, remember these corners are perpendicular. So from here to, let's say, point Q is what? Absolute value of y2 minus y1. And this guy from point Q to R is what? Absolute value of x2 minus x1. So if you use the Pythagoras theorem, what happens is d prime squared is what? This quantity squared plus that quantity squared. But now to find d, what we have to do is what? Take the square root of d prime squared plus this guy, which is absolute value of z2 minus z1 squared. And lo and behold, what pops is this formula. So remember, the distance between 2 points in space is pretty much the same as what? Distance between 2 points on the floor, which is xy plane, except now you have the z component attached to it. Let's take a look at some of the basic graphs, which we will see these graphs over and over in upcoming chapters. In 3 dimensions, so in R3, anytime you have a linear equation in terms of x and y and z, whether what? 2 of these variables are missing or 1 of them are missing, as long as it's linear equation, that means the powers of x and y and z happens to be 1, the graph is called a plane. And a plane is just a flat surface. And it's the simplest surface you can get your hands on. And line is the simplest curve you can get your hands on in 2 or 3D. But in 3D, the simplest flat surface or surface in general you can get your hands on is called a plane. Plane is usually shown by either parallelogram or rectangle. So the question is, if you have x is equal to constant, how would that graph look like? Well, the graph would be like what we have here, which is a plane perpendicular to the x-axis at x equals what? C. What does that mean? Suppose if I was asked to graph x is equal to 2. So remember, this is not a point, it's a plane. So if you would go along what? Over your x and y and z axis, like so. So you know the graph is a plane which is perpendicular to the what? X-axis at x equals to 2. So what you do, you kind of draw a plane like so, and make sure it includes what? The point 2. So this is a plane which is perpendicular to the what? X-axis, and incidentally it's parallel to what? YZ plane. So it will be parallel to YZ plane, you know, to one of the walls. So y is equal to constant, so that would be a plane which is perpendicular to the what? Y-axis, and is parallel to xz plane. So you would kind of like go like this. Okay, so there. So the plane is perpendicular, when y is equal to constant, let's say c, the plane is perpendicular to the y-axis, but it's parallel to what? Xz plane, correct? And this guy, z is equal to constant. So that would be like the same as what? A plane. Remember, we show the planes by a parallelogram or rectangle, which happens to be what? Parallel to the floor, xy plane, and it's perpendicular to the z-axis. So these are planes. So the question is, remember we said any linear equation in terms of x and y and z, or any of these variables, happens to be a plane. So remember, y equals what? Equals x is not a line, but in 3-dimension. So these are all in 3D. They happen to be what? A plane. So they are not line anymore. So how does the graph of y equals x look like? Well, let's see now. On the floor, the graph is a line. But the fact z is missing, that doesn't mean z is what? Is 0. That just means z could be any real number. So what we do, we extend this line, what? Along the z-axis, and lo and behold, we get this plane, which is attached to the z-axis. And this is a plane, y is equal to x. Notice it makes a 45 degrees with the what? XY plane. Do you see it? So the graph is no longer a line, it's a plane. Do you see it? Y equals z is not a line. Yes, on the YZ plane, that means on one of those walls, the graph is a line. But in R3 is a plane because it's a linear equation in 3-dimension, correct? So what do we do? Well, if this is z, this is like, let's say, y. Is that right? Yes. In YZ plane, you get a line, right? You get a line like so. But remember, x is missing, so that means x goes between -infinity to infinity. So the graph is going to be, once again, a plane. So there you have it. Let me just make sure it looks pretty, and then we go from there. Okay, there you go. There, right? Finally, x equals z on the what? XZ plane, the graph is a line, but remember y is missing, so that means y goes from -infinity to infinity. So here's how the line looks like, but remember y is missing, so you're going to extend this along the y-axis, and lo and behold, the graphs in all 3 cases has to be a plane, not a line. Now, y is equal to x squared. You and I, we both know if you are in what? 2-dimension, because the minute z is equal to 0, that means you're on the floor. What's the meaning of that? That means you're on the xy plane. Okay, so you and I, we both know the graph on the xy plane happens to be a parabola, which is a curve. But the minute you put this in R3, you graph this guy in R3, the graph is not a curve anymore, it's a surface. How? Well, here is y-axis, here is like z-axis, here is the x-axis. On the floor, the graph looks like a curve, like so. Is that right? But notice z is missing, but that doesn't mean z is 0. That just means z goes from -infinity to infinity. So what you do, you kind of extend this curve along the z-axis like so, and lo and behold, you get a surface. And we call this cylindrical surface. Okay, cylindrical surface. Why do we call it cylindrical surface? Because it kind of looks like a cylinder, but it's not closed. So it's a cylindrical looking surface. What about this guy? X squared plus y squared equals 4. Well, remember you are in R3. So, excuse me. On the floor, this would look like a circle, right? But in the space, it's not a circle anymore. Be careful. Excuse me. Notice z is missing, so that doesn't mean z is 0. That just means z goes from negative infinity to infinity. So the graph in 3 dimensions, let me just squeeze the graph right over here. Notice on the floor it's just a circle, correct? But z is missing, so you have to extend the circle along the z-axis, and lo and behold, you get something called cylinder. So the graph of what? The sum of the square of 2 variables in R3 is rain or shine, a cylinder. Sometimes cylinder what opens, kind of stretches along the z-axis. Sometimes it stretches along some other axis. In this case, y is missing, so y goes from negative infinity to infinity. Remember, these kind of equations, the graph is called cylinder. Okay, so what you do, you kind of graph your 3-dimensional axis. So here is what? Incidentally, the radius here was 2, whereas here the radius is 3, so you kind of go like this. Okay, but remember y is missing, so you extend this guy along the y-axis, and lo and behold, you have a cylinder lying along the y-axis. Do you see it? So sometimes you have a pair of equations, and we will talk about these in upcoming chapters, but this is like a preview attraction. If you are given in this section a pair of equations, you can bet your money that would be the equation of a line in 3D. Why is that? Here's a fact. 2 planes intersect each other in a line, whereas 3 planes intersect each other at a point. Okay, if they do intersect. Excuse me. So the question is, each of these guys is a plane. So remember, when x or y or z is constant, these are planes. Planes are like what? Also known as flat surfaces. So if you intersect 2 planes, the result is a line. It is just like, you take 2 planes like so. I don't know if I can show it to you guys. Take 2 pieces of paper and then intersect it. I don't know if this is working out, so never mind. So the intersection of 2 planes happens to be a line, yes? So if this is 2 planes, the intersection happens to be a line. So, so this would be a line parallel to the what? Y-axis. So when x is equal to 3, that's the graph of x is equal to 3, the plane. This guy is what? Z is equal to 1. So the graph happens to be a line which is parallel to the y-axis. And it also goes through many, many, many points. One of those points happens to be 3, 1, 3, let's say 0 for y and 1 for what? Z. So it's one of those points. Remember, we have infinite many points on the line. So the other one could be like, I don't know, 3, let's say 2, 1. So remember, y goes from what? Negative infinity to infinity. Later on, we will see the parametric equation of this line is given as x is equal to 3, y is equal to what? A variable, because t goes from negative infinity to infinity, but z is 1. So the line goes through the point, what? 3, and this would be like 0 plus t, 3, 0, 1, and it's parallel to the y-axis. So t is called parameter, And don't panic, we will learn all about this in, I think, section 12.5. What about this guy? X equals 1 is not a point, it's not a line. These are in plane. These are planes in what? In R3. And remember, two planes intersect each other at a what? At a straight line. In this case, the line is parallel to the what? Z-axis. Notice whatever the variable is missing, the line will be parallel to that missing axis. And notice the equation of the lines are given by pair of equations, not just a single equation. All right. The equation of the sphere. So we already did pair of equations. So let's get right into what? Spheres. Spheres, either they have the equation of x squared plus z squared equals r squared. Notice it's just like the circle in what? In 2 dimension, except now we have to add z to it. Or you have what? X minus a squared plus y minus b squared and z minus c squared equals r squared. In this case, both of these, the graph of both of these guys are called sphere, like a basketball. But in this case, the center is at 0, 0, 0, and the radius is r. Here, the center is at ABC, and the radius is still r, which is the square root of the number on the right side. So in this case, this is called sphere. The center is at 0, 0, 0. Radius is the square root of 9, which is 3. So how would you graph a sphere? So you kind of go, okay, here's my three-dimensional space. The center is what? At the origin. So here is kind of like 3. And to make it look like a what? Sphere, we kind of do this. And now we have a sphere. You see it. Here, the center is at 1, 0, 3. The radius is still what? The square root of 9, which is 3. The way you do this is the easiest way to do this is what? Kind of like translate your axis from what? 0, 0, 0 to 1, 0, 3. In other words, if this is your original axis, translate this to what? Translated axis like z prime, what? Y prime and x prime. But remember, the origin is no longer at 0, 0, 0, is at what? 1, 0, 3. Okay, and then now you graph your sphere as before, but make sure people know that your center has been shifted. You see it. So this is like a shifted what? Sphere. Sometimes you're asked to graph inequalities. Notice the fact it says x is greater than 0, y is less than or equal to 0, but z is 0. The minute you see z is 0, that means you're on the floor. What does that mean? That means you are on what? On the xy plane. Okay. And the only quadrants that I know, x is positive and y is negative. It has to be right about here. X is positive, y is negative. But z is 0, so that means we're on the floor. What about this guy? X goes between 0 and 1, y goes between 0 and 1, z goes between 0 and 1. Believe it or not, that would be the graph of a cubic. Okay, like so. Each side of the cube happens to be equal to 1, right? So this is like x goes from 0 to 1, y goes from, let's say this is y-axis, let's say this is z-axis, let's say this is x-axis. These are all equal to 1 unit. Because x goes from 0 to 1, y goes from 0 to 1, what? Z goes from 0 to 1. This would be a cubic in what? In first octant. You see it. Everything is positive. What about inequalities? Remember, this is kind of like a sphere, but what does it mean to say it's less than or equal to 1? Remember, the center is at 0, 0, 0. The radius is square root of 1, which is 1. So the fact you have an inequality, greater than means inside the sphere, less than means inside the sphere, greater than means outside of the sphere. So what you have here is a sphere, correct? Okay. And you include the boundaries because it's what? Equal sign. So the boundaries, these are called boundaries, should be solid. And then you have to shade what's inside the sphere. Do you see it? Whereas here, you don't include the boundaries. Okay, so it would be like a dotted line kind of a deal. Okay. And you are outside of the sphere because it's greater than or equal to 1. Remember, the center in both cases happens to be 0, 0. The radius is 1. Do you see it? Here's the center, here's the radius. Right? Then we got distance problems. So this would be like distance between a point and the coordinate planes, like, you know, xy plane, yz plane, and xz plane. It just so happens if you have a point, like let's say xyz, and you want to find its distance from the floor, notice this has to be the shortest distance, so you can't just choose any point. It has to be the shortest distance. So the corresponding point to xyz on the floor is xy0. So if you use the distance formula, what? You will have 0 for x component, 0 for y component, but z1 stays. So the answer would be absolute value of the what? Z component of the point. The distance between a point and xz plane, it will be absolute value of the y component of the point. And yz plane would be the absolute value of what? X component of the point. So here, example is here's a point in a space. What would be its distance from the floor? So according to our findings, the distance has to be absolute value of 2, which is the absolute value of the what? Z component. The distance between a point and a plane. Well, let's say the plane is a constant. Let's say x equals 4, y is equal to 3, z is equal to -6. What would be the distance between these guys? Well, here is an example. Suppose you have a point in space. You want to find its distance from this plane, but the equation of this plane happens to be z is equal to -1. So what you do, you put what? Select the point right below this point P1, namely -2, 1, -1. Remember, the x and y components have to match, and the z component has to match the what? Value of the equation of the plane. So the x and y has to match the what? The P point. And the z component of the point, because the point is on the plane, so its z, regardless of what x and y is, has to be -1. Because remember, this was given to us. So anyways, if you use the what? Distance formula, so x's disappear, y's disappear, -2, you know, -2, 1 -1, but you only get what? The difference of the z's. So the final answer is what? The distance would be always absolute value of the what? Z component minus the equation, the value of the equation of the plane. So in this case, the D would be absolute value of, remember, this is x1, y1, z1. It would be like 4 minus, what was the equation of the plane? -1. So that would be absolute value of 5, which is 5, which we also got that answer, if you notice, by using the distance formula. Finally, the distance between a point and the x-axis. Remember, this has to be the shortest distance. So if you have a random point x1, y1, z1, the shortest distance on the x-axis below the point is x1. You remember the x values have to match, but y and z are 0 because you're on the x component. So it turns out the answer is what? Square root of y1 squared, z1 squared. For y would be square root of what? X1 squared plus z1 squared. For z, it will be what? X1 squared plus y1 squared. Do you all see it? So that's basically how you find the distances. Okay, sometimes the equation of the sphere is given to us in terms of general form. So the question is, by looking at this equation, can you find the center and the radius of the sphere? Well, what we have to do is what? Kind of like complete the square here, like so. Okay, there you have it. So group the x's, group the y's, group the z's, and complete the square. To complete the square, make sure the coefficients of y square and z square, because remember x square is already been completed, so I just have to complete the square on y and z. Make sure the leading coefficient for these guys happens to be 1. Okay, if you remember from algebra classes, we divide this guy by 2 and square it. Negative 6 divided by 2 is negative 3 plus 1. Square it is 9, so you add 9 to both sides. Divide this by 2 is 4. 4 squared is 16, so you add 16 to both sides. So now you factor these guys out, so you get y minus 3 squared. Z plus 4 squared equals 25. Now I can pretty much tell you this is going to be sphere with center at 0, 3, negative 4, and the radius is the square root of 25, which is 5. You see it. So a couple of more problems, and then we're almost there. Find the equation of a plane and a line in R3. Equation of a plane, find the equation of a plane through the point this and parallel to the what? XY plane. So remember what's happening is this. You have this plane which happens to be parallel to the what? XY plane, which is the floor. Okay, but it goes through the point 3, negative 1, 1. Remember, a plane parallel to the xy plane happens to be z is equal to constant. So that would be the equation of a plane which is parallel to the floor. Okay, so in this case, z is equal to 1 is the equation of this plane. Where did you get 1 from? From the z component of the point. So no matter what point you select on this particular plane, it has to be always 1 unit above the floor. So the equation of this plane is equal to what? X equals 1, but keep in mind, x and y happens to be going from negative infinity to infinity. So this is just a portion of the plane. So the plane extends back and front and sideways. Find the equation of the line. Remember now, this is the equation of the line through this and parallel to the x-axis. So remember here, we need pair of equations, and those equations happens to be 3, y equals 3, and z equals negative 1. Why? Because x is equal to what? It's going to be parallel to the x-axis. So if this is like, let's say the axis, z and y and x. So this is 1, 1, 2, 3, 1. Here's the point. But we like to write the equation of a plane which is parallel to the what? X-axis. So remember, equation of a line shows up as a pair of equations. So no matter what you do, no matter what x is, y is always 3, and what? Z is always negative 1. So that would be the pair of equations. In chapter 12.5, we will see the actual equation is what? X equals t, y equals what? 3, z equals -1, where t goes from -infinity to infinity. This is called parametric equation of a line, which we will see in 12.5, so don't panic. Finally, we got midpoint formula, which is what? The average of the x and y and z components of the endpoints of a line segment. So this would be a line segment. Okay, so if you find the average of the x and y and z components, that would give you the midpoint of a line segment. So here's a nice question. You have a sphere, correct? Okay, there it is. Write the equation of a sphere if one of its diameters happens to have these two endpoints. So let's say this guy, I'm just making this up, let's say this guy is 5, 4, 3, and let's say this guy, here's the center, this guy is 1, 6, -9, and here's the diameter, correct? Diameter connects to what? Goes through the center and connects 2 points on the sphere, correct? Just like circle. What's the equation of this guy? Well, to find the equation, I need to find a couple of items. First, where is the center? And two, what's the radius, correct? To find the center, I know what? The center happens to be midpoint of this line segment, the diameter. So I find the average of the x's, average of the y's, average of the z's. So this would be 1 plus 5, which is 6. 6 divided by 2 is 3. 4 plus 6 is 10. 10 divided by 2 is 5. -9 plus 3 is -6. -6 divided by 2 is -3. There goes the center. Okay? So now I need to find the radius. Radius is the distance between, let's call this A, let's call this B, is the distance between CA or CB. It doesn't matter. So what we're going to do is what? Find either of these distances to find the radius. So I'm going to use CA, the distance between points CA. So what was C now? That was 3, 5, -3. So this would be square root of what? 5 minus 3 is 2. 4 minus 5 is -1. And 3 minus 3 is 6. So 5 minus 3, 4 minus 5, 3 minus 3. So the answer would be 4 plus 1, 36. That's the square root of, what is it? 541. So, because the center is no longer at what? At the center, so the equation is x minus a squared, y minus b squared, z minus c squared equals r squared. So in our case, ABC happens to be 3, 5, -3. So that's x minus 3 squared, y minus 5 squared, z plus 3 squared, and then you have to square this guy. Remember, that's r, so that would be 41. And that's the equation of that sphere. Thank you.